All right, good afternoon, everybody. Handouts just arrived for anyone who was waiting for them. So let's get started. So a couple reminders, first of all, is the checkoff that's due on Wednesday for Lab 2. Lab 3 is due on Thursday, and even though it's a little bit early, I want you to start putting on your radar that our first quiz is coming up next Thursday. We're going to have a quiz review next Tuesday night, and so we'll be sending out some additional information of where that's going to be. And we'll also be providing you with some sample old quizzes for you to work on. All right, so what we're going to do today is continue our discussion from last time, where first we're going to delve into a little bit more of what our hardware looks like for different combinational circuits. So last time we talked about the half adder and the full adder, and then we got into the implementation of multiplexers of different sizes. Today we're going to continue with the barrel shifter, and specifically learn how it is that in hardware we build different types of shift operators. So, we all set with the handouts? All right, great. Okay, so suppose that I want to do a logical shift right by 2, okay? In hardware, it turns out that this is really pretty trivial because all you're doing is connecting the input wires to a different set of output wires. So for example, if I have a 4-bit input, A, B, C, and D, and I want to shift it to the right by 2, then all I do is I take the most significant bit, which is bit 3, and I attach it to the output of bit 1. Similarly, I take bit 2 of the input, I attach it to the output of bit 0, and then I shift in 2 zeros for my most significant bits, and my C and D are shifted out, so I lose that information. So let's just take a look at a quick example. Suppose that I had, this 2's complement number 1001, and I wanted to shift it to the right by 2. Then what I would expect to receive at the output is 0010. So far, so good. All right, now suppose that instead of doing a logical shift right, I want to do an arithmetic shift right. How does my hardware change? The hardware stays pretty much the same, except that in this case, instead of shifting in zeros, what I'm going to do is I'm going to shift in my most significant bit. And we've seen this already in recitation in terms of how to work with 2's complement numbers, but this is what you would actually have to do in your hardware. And so let's take a look at an example here as well. And so if you recall, arithmetic shifting is useful in order to do multiplication and division by powers of 2. So specifically, let's say that I had the number 1000, which in 2's complement is -8, and I wanted to divide it by 4. That's equivalent to doing an arithmetic shift to the right by 2. And so what I end up with is 1110, which in fact is -2 in 2's complement. Okay, and so once again, it's just wiring your inputs to particular outputs in order to achieve a shift of a particular fixed size. So now let's take that a little bit further, and let's say instead of just doing a fixed size of shifting by 2, I want to shift by n, where n can be anywhere between 0 to 31 bits. So how am I going to implement that? Any ideas? We'll start with a very straightforward way, which is let me build, 32 shifters and take a multiplexer that picks between these 32 shifters. So I have, one shifter that's shifting 0 positions, the next one is shifting by 1, and so on all the way to 31. And then I have this really large multiplexer which is picking which of the shifter outputs I want based on the number of bits that I want to shift by, and that produces my output. So is that going to be a valid circuit? Anyone see any problems with that? Yeah, it'll work. But if we think about, how big this circuit is, one way to analyze it is to think about how many two-way one-bit muxes would we need in order to implement this, okay? So at the end of lecture last time, we learned that if you have an n-way mux, you can build that using n-1 two-way muxes, right? So for example, suppose I wanted to build an 8-way mux, I could build it by having 4 two-way muxes over here. Those are my 8 inputs, and then I select between those 4 and these 4, and finally I select between these, and this gives me my 8-way mux built out of two-way muxes, okay? And so the number of muxes that you need in order to build an n-way mux is going to be n-1. Now, in addition, this number that we're trying to pass through here isn't a single bit. It can be as large as n bits. And so we have to replicate this hardware for each one of our bits. And so the size, as far as how many, two-way multiplexers we need in order to build this, is n times n-1, or n squared, which is really very, very large. So obviously we want to think about, can we do better than this? So let's think about how we can do better. Well, it turns out that in general, when we're thinking about hardware, we're always going to be thinking about trade-offs, okay? So the previous design was humongous, but the cool thing about it was that in one single step, I was able to shift any value from 0 to 31. But so let's say that I'm willing to give up a little bit on time, and instead, in order to reduce some of my area. So what could I do? What I can do is I can take my shift and I can break it down into several steps, where the number of steps that I would have is log-based n, and I would have a bunch of fixed length shifters of size 1, 2, 4, etc. of powers of 2. So how would I use that? So suppose, for example, that I want to shift by 5. The way that I would shift by 5 is I would first shift by 4, and then I would shift by 1, and that would achieve a shift by 5 in 2 steps. So looking at a quick example, suppose I have this 8-bit binary number right here. In order to shift it to the right by 5, I would first shift it to the right by 4, and then shift it one more bit, and I would achieve my 5-bit shift through 2 steps with just these 2 shifters. And so in general, you'll see that just using 5 bits, I can encode, which shifters do I need in order to implement any number of shifts from 0 all the way to 31 bits. So for example, if I want to shift by 3 bits, this is going to tell me that I want to shift by 2 to the power 0, which is 1, as well as 2 to the power 1, which is 2, but I don't want to shift by the larger powers of 2, okay? Similarly, suppose I wanted to shift to the right by 21, I would want to shift to the right by 1, not shift by 2, shift by 4, not shift by 8, and then shift by 16 in order to get a shift to the right by 21. Okay, so basically what this is saying is that if I encode using 5 bits, which is what I need in order to encode the number 0 through 31 in binary, then it's going to tell me which of these power of 2 shifters I should use in order to achieve my complete shift that I'm trying to achieve. So this is an example of where we're trading off multiple steps in order to reduce the size of our circuit. All right, so what is my circuit going to look like in order to achieve this? So what we said is, if in my shift value I have a 1, then that means that I want to actually perform the shift. If I have a 0, then I don't want to perform the shift. So what I need is a circuit that's going to do a conditional shift, and this is what it looks like. So here's an example of a circuit that's going to do a conditional shift by 2 bits. And what happens here is if S is equal to 1, then I do perform the shift, meaning that my inputs are 0, 0, AB from the original value of ABCD. And if my shift value is 0, then I don't perform the shift, and so I just keep my inputs the same as they were. And that means that my output is going to be equal to my input in that case. Okay? So how would I express this in blue spec, excuse me? What I would say is if S is equal to 1, then what I'm passing to the output is a 0 expressed as a 2-bit binary, so 0, 0, followed by A, followed by B. And if I don't take the shift, then I just take my original inputs, which are A, B, C, and D. Any questions about that? Great. All right, so now let's take this, the last step, which is to actually build a logical right shift circuit that can shift anywhere from 0 to 31 bits. And so what I'm going to need, or actually it can be 0 to n bits, and what I'm going to need is a bunch of shifters of sizes of powers of 2. And the number of shifters that I'll need is log base 2 of n. So if, for example, here I'm just showing a picture of being able to shift by 1, followed by a shifter of being able to shift by 2. Okay, so this is allowing me to do a shift of 0, 1, 2, or 3, the circuit as I've shown it right here. Now, in addition to having the shifters of powers of 2, I also need to have a multiplexer for each of my shift conditionals. And so that's going to specify, am I taking that shift or not? And so I have one multiplexer for S0 saying shift by 1 bit or not, another multiplexer for shifting by 2 or not, and so on. You can see that I can augment this in order to shift by 4, 8, and so on in order to build as large of a shifter as I want. And so if S, is a 2-bit value, which is S1 and S0, the way that I would express this in blue script is simply as 2 conditionals where the input of the second one depends on the output of the first. Okay, so let's take a closer look at that. So suppose my input, once again, is a 4-bit value, A, B, C, and D. The output of my first multiplexer is going to depend on the value of S1, which is the most significant bit of my shift value. And so it's going to say, should I shift by 2 or not? If I do want to shift by 2, then it's going to produce 0, 0, AB on my output. Otherwise, it's just going to keep my original input. Now I take this new value, temp, and I use that as the input to the next expression. And so here I'm deciding based on S0, am I shifting by 1 bit or not? And so if I'm shifting, then I shift in 1 bit of 0, followed by temp 3, temp 2, and temp 1. If I don't shift, I just keep temp as it was. Okay? And so you can see that by just adding a few more similar expressions, you can create a much larger shifter circuit. And just wanted to mention that, of course, I could have also chosen to write temp 3, temp 2, temp 1 as temp 3 colon 1. But I wanted to look as much as possible like the previous one. So is that clear to everybody, how we build a logical right shift circuit using log n shifters? Excellent. Okay, so now we're going to move on to the next topic for today, which is Boolean optimization. So now that we've seen, how we take some Boolean expressions and convert them into circuits, we want to think about, well, how can we make these circuits more optimal? What do we mean by that? We mean, can they be faster? Can they be smaller? And so the first thing that we're going to do in order to try to achieve that are what we call Boolean optimizations. So we saw already that any combinational function can be expressed as a truth table. And I've given you this truth table here as an example. And I can then convert this truth table to a Boolean expression. And the way that I converted it to this Boolean expression is I simply took the rows that have a 1 in the output and produced a product term corresponding to the values of each of the inputs in each of those rows. So looking just at this row, for example, we have C equal to 0, B equal to 0, A equal to 1, which is C bar, B bar, A. And then we OR all of those together. Okay, so we saw that this is called the sum of products representation of our circuit. And specifically, when we do this mapping without any kind of optimizations, this is called the normal form of our function. So the normal form, what's nice about it is it's unique. What's not so nice about it is it's not optimal because there may be simpler expressions for the same function. Okay, so today we're going to now focus on what kinds of things can I do in order to simplify my Boolean expression that's representing this function. And in recitation, a few times ago, you should have seen this list of Boolean properties. And what we're going to do is we're going to apply these Boolean properties to our expressions in order to try to remove variables that we don't care about, or if we know that an input is 0, then it can cancel terms out, things like that. And using that information, we can basically end up with simpler expressions. So I want to point out, and I apologize that the overbars are not great here. In the PDF that's online, it's easier to see. But I just want to point out a couple of these ones towards the bottom, which are really, really useful, right? So suppose that I have a product term that says A and A bar. Right? It's impossible for that to be true. And so that I know that I can replace that product term with a 0 and basically eliminate that product term from my expression. Similarly, if I have A or A bar, I know that that's equivalent to 1. And so again, an opportunity for optimization. Another very common one, which we're going to see in use in the next slide, is this reduction one. And what this one says is, suppose that I have A, B, or A, B bar. That's equivalent to A ANDed with B or B bar. And using what we just learned, which is that this is equal to 1, this is equivalent to A. Okay? And so we're going to use this property over and over again in trying to simplify our normal form Boolean expressions into much more concise Boolean expressions. So we talk about a minimal sum of products, which is a sum of products representation that uses the smallest number of input gates, of AND and OR gates, and not only the smallest number, but also this tries to minimize the number of inputs of each of these gates. And so now if we take a look at our expression that came from our truth table in its normal form, and we apply these Boolean algebra properties to it, we see that we can start off by merging these two middle terms, because we have CB A bar and CB A, and so the A doesn't matter. A doesn't matter, and so I can just turn that into a single term, which is CB. Okay? I can then continue and further reduce this by merging these two terms and see that in this case B doesn't matter, and so that reduces to the term C bar A. Okay? And so what have I done? I've created a much simpler Boolean expression for y, which produces exactly the same functionality, but it's going to require many fewer gates and also potentially smaller gates. Okay? And so this is what we're going to well, we're not going to do it, actually. We'll initially show you how to do it, but actually we're going to rely on tools to do this for us in order to simplify our circuits and produce, circuits that are as optimal as possible. So one thing, though, that I wanted to highlight is that unlike the normal form representation of the Boolean expression that represents a truth table, the minimal sum of products representation is not unique. Okay, so depending on which Boolean properties you apply to your original expression, you might end up with different sum of products that are of the same size. So the point being that a minimal sum of products is using the smallest number of gates, but there may be more than one minimum sum of products for a particular function. All right, now another way to think about, doing some of this reduction is to rewrite our truth tables using don't cares. So what do I mean by that? this again is the same truth table we've been working with. And if I look here at the first row and the third row, I see that the only difference between them is that B in one case is 0 and in the other case is 1. C is 0 and A is 0 and the output is 0 in both of them. So I can express those two rows together by saying 0, I don't care what B is, 0, and then an output of 0. Right? Similarly, I can combine this row, the second row, with a fourth row by noticing that if C is 0 and A is 1, and I don't care what B is, I'm going to get an output of 1. Okay? And so what this is going to do is, by using this don't care representation of the truth table, it's going to highlight to us what are the reduced terms that we basically can use in order to express this function. So specifically, if I look at my 1 outputs in this don't care truth table, I can immediately say that this corresponds to the term C bar A, because it tells me that I don't care about what the value of B is. Okay? Similarly, if I look at this row, this tells me that it corresponds to the term CB, and I don't care about the value of A. Okay? Now, one thing that you'll notice though is that if you look at this truth table representation, there are multiple rows that can refer to exactly the same set of inputs. So for example, let's say I wanted an input which was 0, 1, 1. 0, 1, 1 is covered both by this row and it's covered by this row. So first of all, it must be the case that if I have such a situation that I'm producing the same output in both of them, and it is, so that's good. But in addition, what that means is that there might be extra terms here which are unnecessary. So specifically in our example, we ended up with an expression that just consisted of C bar A or CB. And now all of a sudden we have this extra term. So why is it that we have this extra term? Well, if I take a look here at what this term covers, it handles the case 0, 1, 1. Well, 0, 1, 1 is also covered by this term right here. And it handles the case 1, 1, 1. And it turns out that case is also covered by this row right here. So because I've already covered both of those cases using my other terms, I don't actually need to include this product term in implementing the circuit, and this is actually just an extra redundant term. Okay? Any questions? So let's continue with other types of optimizations. So suppose you have this function that looks like this, and this is minimal sum of products representation. But now I tell you that I don't have a 4-input OR gate available in order to build this the way you would normally build it, right? Normally, if I wanted to just do a straightforward implementation, I would have 4 2-input ANDs, one for each of these product terms, and then a 4-input OR gate that takes the OR of those 4 AND gates together. So suppose that you don't have a 4-input AND gate, and instead you only have 2-input AND and OR gates. How would we go about implementing this function? Well, I can divide it into multiple steps, okay? So what could I do? I could create an intermediate value, let's call it x1, which consists of the ORing of these first 2 terms, and then x2 consists of ORing of the second 2 terms, and then if I take the OR of x1 and x2, I get exactly what I wanted. But if we take a closer look at this, all of these gates are only 2-input gates, okay? And so what this circuit looks like is something like this. All right, so what have I achieved? I have managed to map my Boolean expression to the types of gates that are available to me, which in this case were only 2-input gates. But it has an implication. What's the implication? If we just did a straightforward implementation, I would have one level of logic that's for my and then I would have one level of logic for my or. Whereas in this implementation, I now have additional levels of logic. So the idea, the issue is that I'm no longer necessarily able to implement it using just two levels of logic if I add this additional constraint. So it's okay though. It turns out that, you know, in our processors we have many, many levels of logic that are being used. In fact, typically we use about 8 levels in our fast microprocessors, and we have as many as 18 in our slow ones. Okay, and so you're going to see these large circuits where, in order to do different kinds of optimizations, or in order to map to the types of gates that are available to us, our logic implementation is going to be more complicated than just a bunch of ands followed by an OR gate. All right, the next type of optimization we're going to talk about is common subexpression elimination. So what does this mean? We're going to start off with the same exact function, except this time the way that we're going to map it into gates is by looking for a common subexpression. And so we can notice that both these first two terms and these second two terms use A or B in them. And so I can rewrite this as A or B ended with C, or A or B ended with D. Okay? This in turn can be rewritten as follows. So I can have an intermediate value x, which is A or B, and then my function now can be expressed in terms of x as xc or xd. All right? And so what does this circuit look like? It looks like this. So once again, you know, I've produced more than 2 levels of logic. So certainly we have to keep in mind that common subexpression elimination might increase the number of levels of logic. But there's one other thing that happened here, which is important to note, which is that until now, all of our circuits have been of a tree structure. And once I introduced this common subexpression, I turned this into an acyclic directed graph rather than a tree, okay, which makes you know, applying some of the other optimizations potentially more complex. And so this is just something that we need to keep in mind when we're actually applying common subexpression elimination. And the last thing is that there is no well-defined optimum for doing these kinds of multi-level optimizations. And so you see that depending on, you know, how we go about it, we might end up with a different circuit that achieves the same functionality but with a different number of gates and with different behavior in terms of the physical properties of those gates, which we'll get to in just a second. And so that's what leads us into our last topic for today, which is logic synthesis, okay? And so we've started off describing our combinational circuits using truth tables, which have a one-to-one correspondence with a basic Boolean expression when you're not considering any optimization in there. And so in the normal form, it's a one-to-one correspondence. We then looked at, well, what kind of Boolean optimizations can we make in order to simplify those Boolean expressions, and then that way be able to implement the function using fewer and smaller gates. And now we're going to go on to look at the more general problem of how it is that we convert our functions into a hardware circuit, and what exactly is involved in doing that. So when we talk about combinational circuits, we know already that it has some function that's associated with it, which is expressed via the truth table. Okay? But in addition to describing the functionality of this combinational circuit, there's 2 other properties, actually there's even more, but we're going to focus in this class on 2, which are area and propagation delay. Okay? And these play a big role in determining what gates we ultimately want to map this combinational function into, okay? And so what does this mean? Well, area is pretty self-explanatory. It basically tells you, you know, how big of a circuit am I going to be producing. And propagation delay is a little more complex. It's basically telling me how long does it take from when I have a valid, or all my inputs are valid, until my output is valid. Okay? And so both of these properties are basically derived from the properties of the gates that we actually use. And so what's going to happen is that we're going to need to take our Boolean expressions, and we're going to need to map it to a particular CMOS, which stands for, complementary metal oxide semiconductor. You don't need to worry about that. But it's just a particular technology which has a set of characteristics or details associated with it. For example, you know, the area that's consumed by each gate, and the power that's consumed by each gate, and the delay that's consumed by it. So what do I do with that? So suppose that, you know, I have a more complicated combinational circuit now, which is made up of 3 smaller combinational circuits, okay? Well, I want to think about, you know, how I would go about basically analyzing what the properties of this circuit are so that I can, in turn, produce the right circuitry for it. So if you know what the functionality of A, B, and C is, you could all, you know, come up with a functional description for this larger combinational circuit, which would look something like this. And so while this looks a little complex, all it's really saying is that in order to produce this output W, I'm going to execute the functionality of module C on 2 inputs, where the first input is the output of module A with X and Y as inputs, and the second input is the output of module B with the output of A and the input Z. Okay? So that's pretty self-explanatory. But what we want to think about now is the other 2 properties that we started looking into. Okay? So specifically, propagation delay. So how would I go about figuring out the propagation delay of this larger circuit that's made up of multiple smaller circuits? Any ideas? Yeah? Were you raising your hand?
Would you have to take the longest path every time?
Yes. That's exactly right, okay? Because what propagation delay means is that as soon as we have all of our inputs valid, we want to know what's the longest amount of time until all of our outputs are valid, okay? And so even though it's possible that some of our inputs are only going to propagate through the A and the C module, it's not enough to consider just that delay. Instead, I have to consider this longest path and make sure that I give this circuit enough time so that it can propagate through A, through B, and through C in order to produce a valid W, okay? And so the way that I would express the propagation delay of this larger circuit is that I would sum the propagation delays along the longest path, which in this case are A plus B plus C, okay? What about area? What would be the area of this circuit? Anybody want to guess? Well, it's just, for the most part, it's the sum of the 3 areas. However, this is hiding a little bit of reality, which is that we're ignoring the wires, okay? So as your circuits get larger and larger, it actually is the case that wires sometimes take up most of your area, and so we sometimes, for larger circuits, have to worry about that as well. But as a first order approximation, you can think of your area as being the sum of the areas of your smaller individual circuits. Okay, so we said that basically what we're going to be given is a library of cells that are of gates that are available to us. And with this library of gates, yes?
About the area, doesn't you kind of have a factory problem is you're just counting the areas, the amount of stuff taken up on the chip. Like, you can't just put...
Yes, which is why exactly I said it's a first order approximation, and in fact the wires, will actually make it end up being, more of an n squared as you start to get to larger circuits. But for small combinational circuits, you can estimate it by summing up the areas of the individual circuits.
I don't mean wires, I mean the package. Like, you can't just overlay everything. Or, well, I guess maybe sort of, but these things aren't just arbitrary shapes that you can rearrange to put into your square chip.
Sure. Sorry, Kate, you wanted to say something?
I was going to say, so like the way it actually gets laid out in silicon is all of your transistors are roughly in the same plane, but all of your wires are in like multiple layers above that. So it ends up being actually like more of a three-dimensional structure, but your transistors are constrained to be on the silicon, whereas the wires you can make above. And so it really is mostly about like actual, like these standard cells that you can sort of rearrange however. So it does end up being pretty close to your transistors count, gate count, rather than wires.
Okay, thank you. So if we look at this standard cell library over here, we've got information about the delay, which is measured in picoseconds, as well as the area, which is measured in microns squared. And the types of gates that are available to us in this particular example are, let's say, an inverter, which has a delay of 20 picoseconds and an area of 10 microns squared. And here we've got a bunch of two input gates. Now, if I look at the numbers associated with these two input gates, the first observation that I want you to make is that in current technology, inverting gates are smaller and faster than non-inverting gates, okay? And so typically what you'll see is that when we actually go to convert our circuits into gates, you're going to see a lot of these inverting gates, the NANDs and NORs, used in the ultimate structure of the circuit that is created. The second thing I want you to observe is that when we have four input gates here, which are, clearly larger than our two input gates, this is a property that that is in fact specific to the number of inputs. And so as the number of inputs grow, our delay and size grow as well, okay? And so we're going to need to take both of these constraints into consideration when deciding which gates to map our expressions to. In addition, there's going to be potentially multiple gates that do exactly the same thing. So suppose, for example, that I have a product of A, B, C, and D. One way that I could implement that, using the gates that were available to me in the library that we just took a look at, is as a four-input AND gate, okay? And these are the values that were in that table, which tell me the propagation delay of this four-input AND gate is 90 picoseconds, and the size is 40 microns squared, or 40 squared microns. Alternatively, I could have created this product term using a four-input NAND gate followed by an inverter. If I did that, I actually would end up with exactly the same constraints in terms of delay and area. But here below, we see yet another implementation of a four-input AND gate, and I'll show you in a minute how this actually turns into a four-input AND gate. But as far as looking at the delay and area associated with this circuit, well, we see that the delay is the longest path, which is going through a NAND gate plus a NOR gate. And so our propagation delay ends up being 65 picoseconds. And the area needs to account for all of the gates in my circuit. And so I need to account for two NAND gates and a NOR gate. And so I have an area of 46. Okay? So what do we see here? Well, we see that this particular implementation of the AND of four inputs is faster than both of the cases above. But we had to pay a price of a slightly larger area in order to do it, okay? And so depending on what it is that we're trying to optimize, we're going to choose to map our functions into different gates. So just before we continue, let me just quickly show you proof that this is in fact a 4-input AND gate. And so in order to do that, we used De Morgan's law, and you're going to find that we use De Morgan's law a lot. And so what De Morgan's law tells us is that a NOR gate, which is A or B bar, is equivalent to A bar ANDed with B bar, okay? So another way I can draw that is an AND gate with its 2 inputs inverted. If I replace this NOR gate with this gate, I end up with something that looks like this. Oh man. And basically, these inversions cancel each other out. And so, in fact, this is equivalent to a 4-input AND gate, okay? Any questions about that? Great. Oops. Okay, so now let's take this example further, and let's say that, you know, I give you a particular circuit, and I give you a library of gates. In this case, you have an inverter, a 2-input NAND, a 3-input, and a 4-input NAND, and we have some area parameters for each of those gates. And what I want you to do is I want you to map this circuit into these logic gates where your optimization goal is to minimize area, okay? So, you know, how would I go about doing that? Well, here I show you, you know, 2 possible implementations of mapping this circuit to the set of gates that are available to us. So if we look at this one over here on the left, what did we do? We just mapped our circuit directly to the basic gates, which are 2-input NAND gates and inverters. Okay, so I ended up with 7 NAND gates, each of which had an area of 3, so for a total of 21. And I have 5 inverters, each of which has an area of 2 for a total of 10. And so together, the cost of this particular coverage of or implementation of this circuit is 31 as far as area is concerned. Now I could have, since I also have 3-input NAND gates and 4-input NAND gates available to me, I could realize that actually the structure here in blue is equivalent to a 3-input NAND gate. And this structure over here is equivalent to a 4-input NAND gate. So if I implement this circuit using 1 4-input NAND gate, 1 3-input NAND gate, and then 2 2-input NAND gates and 2 inverters, I end up with a much smaller area of 19 versus the original 31. Okay? So clearly there's an optimization problem here that, you know, we need to do every time that we're trying to map our Boolean functions to a set of gates. So as you can imagine, this is actually a very complicated problem, and so it's not something that we do manually. And so the things that we need to consider are, we do things like Boolean optimizations. We do things like mapping our Boolean expressions to the particular cell library that's available to us. We can also do things like multidimensional trade-offs. And if you think about any circuit that's more than, you know, a very small circuit, you're going to very quickly not be able to do this by hand. And so instead, we're going to use tools for this, okay? And so this is why we use BlueSpec. So we're going to describe our circuits using a high-level description language, which in our case is BlueSpec. And then we're going to use a synthesis tool, which can take as input our high-level description of the circuit that we're trying to build, as well as a target gate library, and determine what the optimum synthesis of that circuit would look like. So specifically, what our synthesis tool is going to do is it's going to take 3 inputs. It's going to have the high-level circuit description, which describes what it is that our circuit functionality is. It's going to take in a standard cell library, which is going to specify the delay and area and power parameters for every single gate that's available to us. And it's also going to specify, you know, what's the largest number of inputs in the gates that are available to us. And typically you'll see, you know, 2 input gates and 4 input gates, but you probably won't see 8 input gates in these cell libraries. And finally, the third thing that it takes in is what is our optimization goal? Are we trying to minimize delay? Are we trying to minimize area? Are we trying to minimize power? Are we trying to minimize some combination of all of those? Okay? And so based on all of that, it's going to produce an optimized, notice that we say optimized, it's not necessarily optimal, circuit implementation of the function that you described in blue spec. And so with that, I'm going to leave you with this take-home problem to think about and try it out on your own. You'll see it tomorrow in recitation, where I've shown you here a sum of products expression. We want you to use Boolean optimization or Boolean properties in order to minimize this. And then we want you to take your minimized circuit and map it to the cell library that we had on slide 18. And then next time we're going to go on with, oh, actually one more thing that I wanted to say is that as part of your lab 3, you are actually going to use a synthesis tool. So in addition to describing your circuits using BlueSpec, we're also going to have exercises of using the synthesis tool in order to optimize for different constraints. And you'll get a chance to see how you end up with different circuits, circuit implementations of the same function, depending on what your optimization parameter is. All right, thanks everybody. That's it for today.